So this is section 5.2, the characteristic equation. We're going to continue to work with eigenvalues and eigenvectors and explore their meaning a little bit. So recall that a square n by n matrix is non-invertible if and only if its determinant is 0. Let A be an n by n square matrix with eigenvalue lambda. Then there is a vector x different from 0. So this would be an eigenvector. Eigenvector has to be different from 0, such that A minus lambda I times x is 0. Thus, the above equation has a non-trivial solution. So there's a non-trivial solution to the homogeneous equation for the matrix A minus lambda I. So that means A minus lambda I is not invertible. And so if A minus lambda I is not invertible, we can see that the determinant of A minus lambda I is equal to 0. Conversely, if the determinant of A minus lambda I is equal to 0, it must be true that lambda is an eigenvalue of A. So what we proved is a scalar lambda is an eigenvalue of a square matrix A if and only if the determinant of A minus lambda I equals 0. And this will be the key for us to finding eigenvalues of matrices. Normally, from now on, we're going to try to find the eigenvalues first and then describe the associated eigenspaces. But we'll start with eigenvalues. So let's go ahead and apply this idea to this matrix A. We want to try to find the eigenvalues of A. So we need to consider A minus lambda I, which is 1, 2, 8, 1, minus lambda I is going to have, lambda 0, 0, lambda, right, on the diagonal. And so A minus lambda I is 1 minus lambda, 8, 2, 1 minus lambda. And what we're interested in is the determinant of A minus lambda I. And since this is a 2 by 2 matrix, we can just take the product of the entries on the main diagonal. So 1 minus lambda times 1 minus lambda minus the product on the reverse diagonal, minus 16. So I get 1 minus 2 lambda plus lambda squared minus 16, or lambda squared minus 2 lambda minus 15. So lambda is an eigenvalue if and only if this determinant is equal to 0. So we set this equation equal to 0. And this is a quadratic equation that I think factors into lambda minus 5, lambda plus 3. So lambda equals 5, lambda equals negative 3 are the two solutions to that equation. So these are the eigenvalues of the original matrix A. So 5, negative 3 are the eigenvalues for that matrix. The determinant of A minus lambda I is called the characteristic polynomial of A. So in our example, here is the characteristic polynomial of that matrix. And when you set it equal to 0, we call that the characteristic equation. So it's just a subtle distinction, but here's the characteristic equation for that matrix. And the solutions to the characteristic equation are the eigenvalues. Okay, another problem. And So here's a more, maybe a messier problem, a more complicated calculation. But the concept is the same of what we've already done. We want to find the characteristic polynomial for this matrix. And so what we got to do is we got to compute the determinant of A minus lambda I. So A minus lambda I is a matrix. We can just do it all in one step if we realize that this is going to change A by subtracting lambda down the main diagonal. So I'll get minus lambda, 0 minus lambda is minus lambda, 0, 2, 0, 1. I get another 0 minus lambda, so that's minus lambda, 1, 0, 0, 1. Now I'll have negative 2 minus lambda, 0, 0, 0, 0, and then I'll have 1 minus lambda. So we need to compute the determinant of that matrix, A minus lambda I. And to do that, I'm going to use cofactor expansion. I like the way this last row came out. So we'll do cofactor expansion along that last row. So I'm going to have a whole bunch of zeros, right? And then I'm going to have 1 minus lambda times plus or minus 1. What is it? Plus or minus 1. And we go plus, minus, plus, minus, plus, minus, plus. So it looks like it's times plus 1. Times the determinant of the matrix I get by removing the row and column corresponding to 1 minus lambda. So I have minus lambda 0, 2, 1 minus lambda 1, 0, 1 minus 2 minus lambda. And so I have a 3 by 3 determinant that I need to calculate here. And so let's go ahead and do it. So I got 1 minus lambda in front of, now my situation is not as nice as before. Maybe I'll just expand along this first row. So I got to remember to take 1 minus lambda times everything I get here. I got minus lambda times a plus 1 times the 2 by 2 determinant I get by removing its row and column, minus lambda 1, 1, minus 2 minus lambda. Then I get plus 0, and then I'll get plus 2 times a plus 1 again, and times the 2 by 2 determinant I get by removing the row and column of 2, 1 minus lambda 0, 1. So just a bit of an algebraic mess here that we got to work with. Okay, so I got minus lambda times minus 2 minus lambda minus 1 plus 2 times, this is going to be 1 minus 0, I think just plus 2. Minus lambda times, I'm going to get 2 lambda plus lambda squared, distributing here, minus 1 plus 2. Looks like I have 1 minus lambda times minus 2 lambda squared minus lambda cubed plus lambda plus 2. Oh, now I got to distribute. So multiply by 1, multiply by minus lambda. Fourth, minus lambda squared minus 2 lambda. Okay, so now I'm ready to combine like terms. I got lambda to the 4th, and then I got minus lambda cubed plus 2 lambda cubed plus lambda cubed minus 2 lambda squared minus lambda squared minus 3 lambda squared, and minus lambda plus 2. There's the characteristic polynomial. For a 4 by 4 matrix, you would expect to get a 4th degree. The degree of the characteristic polynomial will match the dimension, or the number of rows or number of columns of the matrix. And the point of this one is to just help us see that this characteristic polynomial can get pretty nasty pretty quickly if you're working with a matrix of size larger than 2 by 2 or 3 by 3. There's, theoretically, there's a way to solve any 4th degree polynomial, any 3rd degree, any 2nd, but once you get beyond degree 4, it's actually a theorem of math. There's no formula for solving polynomials of higher degree. So actually, solving the characteristic equation is not always a very realistic way of finding eigenvalues. But there it is. There's our characteristic polynomial for that matrix A. And let's continue on to the next equation, next problem. Find the characteristic polynomial of this matrix, and then find the eigenvalues of A along with their multiplicities. Now, I don't know why I worded it in this way, because I hope you're going to notice right away that this is a triangular matrix. Below the main diagonal, we have all zeros. And in the previous section, we saw that a triangular matrix will always have its eigenvalues along the main diagonal. So we actually know what the eigenvalues are here. The eigenvalues are 6, -2, -2, and 3. And yet I still want to write down this A minus lambda I, which will be 6 minus lambda -4, 1, 0, 0, -2 minus lambda 8, 1, 0, 0, -2 minus lambda 0, 0, 0, 0, 3 minus lambda. So I still want to write out the characteristic polynomial, which, because this is triangular, we know it's going to be the product of the entries along the main diagonal. And just notice that I can factor out a -1 from both of those -2 minus lambda factors. So when I multiply the -1s together, I get +1. And there's my characteristic polynomial. So again, because I had a triangular matrix, I had a shortcut way to computing this determinant, right? Just multiplying the entries along the main diagonal. So there's the characteristic polynomial. Now, we know the eigenvalues, and we actually knew the eigenvalues before. The eigenvalues are going to be 6, -2, and 3, but one point of this is I just want you to see the way we talk about multiplicity. So 6 has multiplicity 1. There's only one factor of 6 minus lambda in the characteristic polynomial. But -2 has multiplicity 2 because that factor is squared, right? The 2 plus lambda factor is squared, just like you talk about multiplicity of zeros of a polynomial. And 3 has multiplicity 1. So while there are just 3 numbers that are eigenvalues of that matrix, if you count multiplicity, if you count -2 twice, it's like there are 4, right? And the 4 matches up with the dimension of the matrix we started out with. Okay, next page. Now, the rest of this section is just a little discussion of some theoretical issues, and let's go ahead and do that. Similarity of matrices is something we're going to work with quite a bit in the rest of the course. So let A and B be 2 square matrices, n by n again, got to be square here. We say that A is similar to B if there exists an invertible n by n matrix P such that P inverse AP equals B. And so what does this mean? Well, remember now, matrix multiplication is not commutative, so please do not be tempted to, like, say this, that you can switch those two, that you can cancel those out and get A equals B. If matrix multiplication was commutative, the only matrices that would be similar to each other are they have to be equal. So that this idea, that's not true. Like, we can't assume that. So you can have different matrices, A and B, where this relationship holds. And remember how we have to be careful when we multiply both sides of an equation by a matrix, we have to do it on the same side of both sides. So just notice if we multiply by P on the left, we obtain AP equals PB. If we multiply by P inverse on the right, we get A equals PB P inverse. And those are just different forms of the similarity relationship, P inverse AP equals B. I call this a little theorem. It's kind of obvious, but it's worth stating. If A is similar to B, B is similar to A. And I wrote out the proof there, and you can just think about that on your own. So we can talk about 2 matrices being similar to each other. And now theorem 4 is like, maybe you might say, well, why would we care about similarity? What's the point? This is meant to help us see why we would care. If 2 n by n matrices A and B are similar, then they have the same characteristic polynomial and they have the same eigenvalues. So similar matrices have the same eigenvalues. Let's go through the proof. Now this proof is kind of interesting, and it's something I would want you to be able to reproduce. I think it's very accessible. So suppose A and B are similar, so B can be written as P inverse AP, where P is an n by n invertible matrix. If we're thinking about eigenvalues, we want to think about this B minus lambda I matrix. B minus lambda I is the same thing as P inverse AP minus lambda I, just substituting this product on the right for B. And then what we're going to do is we're going to write P inverse AP minus lambda, rewrite I as P inverse P, because P inverse P has to be equal to I. And the reason we would do that is, well, let's put one more step in here. I'm going to rewrite lambda P inverse P as P inverse lambda IP. I can move that scalar, the scalar will commute throughout this equation. And I can also insert a factor of I anywhere without changing the values. So this gives me lambda attached to this identity matrix in the center that allows me to work with the P inverse and P separately. And then I can factor out a P inverse from the left, a P from the right of both sides, and I've rewritten that now as P inverse A minus lambda I P. Now, if these 2 matrices are equal, then their determinants have to be equal. But the determinant of the P inverse A minus lambda I P is going to be the product of the determinants of those separate matrix factors. And I guess I continue on the next page. And so we have the determinant of B minus lambda I equal the determinant of P inverse, which is 1 over the determinant of P, times the determinant of A minus lambda I times the determinant of P. But these are just numbers now, these determinant values, so we can cancel 1 over determinant P with determinant P. And we get the determinant of A minus lambda I. So we have the characteristic polynomial of B, which is this determinant, equal to the characteristic polynomial of A, which is this determinant. Thus, A and B have the same characteristic polynomials. Since the eigenvalues are roots of the characteristic polynomials, roots of the characteristic equation, A and B have to have the same eigenvalues. So we're done. Now, this is not an if and only if statement in Theorem 4, so this is a little bit tricky, but kind of important to think about. We're saying if matrices are similar, then they have the same eigenvalues. We are not saying that if they have the same eigenvalues, they have to be similar. That actually is not true. It's possible for matrices to have the same eigenvalues and not be similar. So comments, similar matrices have the same eigenvalues. It is possible for matrices that are not similar to have the same eigenvalues. If two matrices are row equivalent, and this is just sort of a free add-on here, if two matrices are row equivalent, they might have different eigenvalues, so that this business of having the same eigenvalues is something very different from the row equivalence property of matrices. And that's the end of this section.